Welcome to the Explainer. So today we're diving into something genuinely mind-bending. There's a mathematical anomaly hidden deep inside SHA-256, and, unexpectedly, it holds the exact key to solving our biggest, most modern crisis in AI governance. For decades, we've looked at foundational digital systems in a really specific, kind of simplistic way. But this recent research by Dean A. Kulik just flips the whole thing on its head. It takes us on this wild journey, right from the microscopic geometry of cryptography straight into the modern AI boardroom.
Now, usually we think of cryptographic hashes as these chaotic data shredders, right? We just assume you throw data into an algorithm like SHA-256 and it acts exactly like a blender. It just irreversibly destroys the information lineage to spit out this completely uniform randomized string. But what if they secretly house a perfect invisible architecture? What if there's actually a rigid structural topography sitting right beneath that veil of chaos?
Kulik's research frames it perfectly. He states, semantic closure depends on addressed dependency geometry rather than carrier ceremony. Okay, so what does that actually mean? In simpler terms, beneath all that surface-level scrambling of data, which he playfully calls the carrier ceremony, there's a rigid physical geometry holding the whole shebang together. It's not just random diffusion floating around in the digital ether, it's actually a highly ordered structural manifold that dictates exactly how the entire system breathes and operates.
That brings us to Section 1, the illusion of randomness, unveiling the hidden math. Let's really dive into this by looking at how the world's most famous hash function, SHA-256, actually operates on the microscopic level. To see the illusion at play, we need to look past that final scrambled output and examine the actual engine itself.
Just look at the specific deterministic recurrence mathematical schedule operating in SHA-256. This equation isn't just randomly mixing data in some chaotic field. No, it's a highly structured deterministic machine. It's building what the research identifies as a two-rail topology. Basically, it's systematically sorting data into an even and an odd processing rail, rigidly preserved by specific mathematical operators. So it's not a blender at all. You got to think of it more like a precisely calibrated factory assembly line, just perfectly orchestrating every single bit of data.
Which leads us straight into Section 2, the secret K-seam discovered, the load-bearing wall. Deep inside this deterministic machine, researchers isolated a highly specific coordinate pair that acts as the absolute foundation of the entire algorithm. It's literally the exact moment where our digital assembly line undergoes its most critical, fragile transition.
They call this the K equals 16 and 17 seam. Now, I want you to think of K equals 16 and 17 as a load-bearing wall inside a massive digital building. It perfectly controls the flow of parity, forcing the incoming data into these extremely specific geometric shapes. It is internally indispensable. It's the only way the algorithm functions securely. But here's the truly fascinating part. You absolutely cannot see this load-bearing wall from the outside.
This exact seam strictly organizes the data right before the permanent scrambling happens. It acts as the bottom of a graded meat semilattice. Now, I know that sounds like a mouthful, but essentially, it's just a structural funnel that regulates exactly 11 distinct residue classes. It physically prevents the even and odd parity horns from ever crossing paths. If you pull this K-pair out, or even just slightly damage it, the whole rail structure collapses entirely. It is the absolute irreplaceable heartbeat of the schedule's geometric determinism.
And that brings us to Section 3, the Aperture Firewall, invisible at the boundary. Because this raises a massive, absolutely crucial question. If this K-seam is so structurally important, and it completely orchestrates the flow of data inside the hash, why haven't we ever seen it in the final 256-bit output digest? Why on earth does the output still look completely random and uniform to us?
Well, this is the magic trick of the whole system. It's a phenomenon the research calls the Aperture Firewall. See, the internal structure operates flawlessly and deterministically, but the final boundary, the output we actually get to observe, intentionally erases any trace of it. The structural geometry is forced by the system, yet it is perfectly walled off from the external observer. It's essentially an architecture purposely designed to hide its own skeleton.
The proof for this is all on the data interventions. When researchers completely zeroed out position 16 to simulate damage, the standard readout in real SH-256, that first HD_A column you see there, showed absolutely zero anomaly. It maintained total, perfect uniformity. But check out that final delta column. By comparing the real system against a shadow carry-free version, the hidden carry exhaust differential hit exactly -4. Boom! They successfully detected the invisible seam.
So the carry exhaust detects the seam even when the digest boundary totally erases it. The system's internal channels know the geometry is there, and they react to its damage, even while the external output pretends everything is totally fine. But let's zoom out for a second and see how this builds into something much bigger. Because honestly, this cryptographic quirk isn't just about abstract math. It is the exact blueprint for how we must govern high-speed systems in the real world.
Moving right along to Section 4, AI and the Visibility Crisis, the Macro Bridge. You might be wondering, why does this hidden geometric structure inside a 20-year-old hash function matter to us today? How does a tiny mathematical boundary jump to becoming a macro-level framework? Well, it all comes down to speed, observation, and fundamentally, trust.
Think about the commonality here between cryptographic compression like SHA-256 and modern generative AI systems. What actually binds them together? They're both ultra-high-speed systems where internal state transitions evolve vastly faster than a human observer can ever read out. We simply cannot look inside the vortex of SHA-256 as it spins, just as we cannot manually inspect every single neural activation in a massive language model as it hallucinates, reasons, or generates code.
We're currently building AI machines that think and evolve way faster than we can watch. It makes the demand to observe every single internal state transition absolutely impossible. Perfect microstate visibility? That's just an impossible fantasy. We obviously can't pause every microsecond to inspect an AI's logic. But at the same exact time, evaluating the final output alone, just blindly looking at what the AI types back to us on a screen, that cannot guarantee trust. Just like the hash output, that final readout can hide immense internal complexity or even dangerous structural drift.
And that brings us to our final section, Section 5, Trusting the Aperture, the Governance Solution. So if we can't watch the internal states of AI at the micro level, and we can't just blindly trust the final output, how do we practically govern these rapidly evolving systems? Well, we learn from the Aperture Firewall. The solution is exactly how SHA-256 works. We stop demanding impossible microstate visibility, and we shift entirely to what this research calls aperture trust. Instead of trying to somehow freeze every chaotic frame of a trillion-parameter neural network, we have to identify its load-bearing geometry. We find the fundamental structural boundaries that simply cannot be bypassed, and we monitor those instead. Now, to be clear, aperture trust is not blind trust. It means governing AI by continuously checking internal load-bearing structures at the correct monitored boundaries. It's all about calibrated, disciplined confidence. Just as we know that the K-seam strictly regulates the SHA-256 schedule, even if we can't see it in the final digest, we can architect AI systems with verified internal controls. We can build in triggers that alert us the second the model's fundamental operational geometry starts to fail.
And hey, this isn't just theory. As outlined in frameworks like the NIST Generative AI Profile, this is literally the realistic future of regulation. We govern AI by monitoring specific internal invariants. We validate operational boundaries. We measure continuous structural invariants. We monitor for behavioral deviations. We trigger bounded escalation and human intervention only when the system actually exits a validated operating aperture. We don't need to read every single thought the machine has. We just need to ensure the geometric boundaries of its reasoning remain unbroken. The central takeaway from this explainer is summarized beautifully by Dean A. Kulik. He writes, as internal structure accelerates beyond direct readout, trust cannot be assigned to the output alone. The trust object becomes the aperture. In any high-speed system, whether we're talking about cryptographic hashing or next-generation artificial intelligence, trust absolutely must migrate from direct observation over to disciplined structural assurance.
I'll leave you with this provocative thought to chew on today. As our machines continue to evolve, processing information and generating realities that completely outpace human vision, how will we intelligently design the boundaries we choose to trust? We can no longer rely on seeing everything. The future of trust really belongs to those who understand the invisible architecture beneath the noise. Thank you so much for joining me for this explainer.